Well, thank you for having me. So my name is Paul. I'm a senior lecturer in the school, and I've been working closely with Kerry, Chris, and many great people uh, at the ACEMS, the Centre, at Queensland Academy of Sport, Australian Institute of Sport, Swimming Australia, Triathlon Australia, and West Coast Eagles so far to date. Uh, so a bit about me. Besides in the school, of course, I'm with this associated with the centers. Actually, I came from aerospace. Working with kind of complex dynamic systems and this was replicating human expert pilots to automatically plan paths for aircraft. And so I guess a lot of this, my career so far in data science and modeling has been about how can we analyze and model these complex systems. So a lot of work in Bayesian statistics and machine learning, especially state-space models, and applied especially to sports and physiology and in ecology and marine ecology. So what I would like to do is share with you some of our projects that we have done. I can only have time to give a high-level overview, but very happy to have discussions afterwards. I started for me in 2016. I had a national level swimmer who was our student, Nick, and so far we've had over 20, probably closer to 30 now, vacation research, internships, a joint postdoc with QAS and swimming, honor students, and so on and so forth. So this first particular project I want to talk about is about predicting fatigue. So the idea is using the counter movement jump, a functional test. So we, unfortunately, I can't do a jump example for you here online. Uh, it's like you can imagine if you stood on a set of scales and you did a jump, and then you can record the force time curve. And the idea is with this, you can do a couple of things. One, you can characterize athletes based on their abilities. And so the idea behind this was that you use a technique called principal components analysis, and more importantly, functional principal components analysis, to be able to look at and explain what contributes to the most variation in the data. So you can see, so this is just clustering different athletes. So different athletes have different abilities, uh, which relate to their fatigue onset. And one of the powers of this is that, okay, by being able to explain most of the variation of the data, okay, so most of that variation comes from differences between athletes, which might be quite obvious. But it's the smaller differences that relate to metabolic and neuromuscular fatigue. So the idea is short-term versus long-term fatigue. And the idea is that you want training to have short-term fatigue, but not long-term fatigue, so that you're ready for the next training session of the game. And these models allow us to do these kind of predictions. Now, related to this is using anaerobic tests. So this, the calorie minimum jump is like one of these types of tests to track seasonal progression. Are we getting faster, stronger over the course of the season, and ideally to peak at a competitive event, or is it not progressing as expected? And so that was some work with this one with AIS and the other one with Queensland Academy of Sport. Another example I want to talk about is cycling. So this is the cycling component of the triathlon. What you're looking at here is a track, cycling, the latitude, longitude of a cycling track. And on the right is the elevation. So you can see there's some instrumentation error at the beginning of the race. So there's a bit of a hill in this particular race. And what we do is use the data collected from wearable technology and GPS and kind of power output to try to estimate what were the energy systems, whether it's the really high power, short duration ATP or anaerobic systems or aerobic systems. With the idea being, can we characterize the demands of a particular course? So for example, for the new mixed relay triathlon in Tokyo for next year now, what kind of how much anaerobic power do you need to be able to put out and sustain to be able to be competitive? And the flip side of that, of course, is to analyze athletes themselves. How are they performing on current races and being able to benchmark them? So this is this what I'm showing here is some early work, but this is a current project with an honor student in Triathlon Australia. Moving now into different area, swimming. And here we were using machine learning, and especially random forests, to analyze the swimming relay. So this was a key interest of Swimming Australia. There's many medal opportunities here. And what we're interested in is two things: team selection and strategy. So the idea is, depending on your competitor teams, who they have in their team, and who you have in your team in terms of the world ranking of swimmers, but also what order you run your swimmers in. So, for example, do you bookend the race, that first row there, with your best swimmers, the fastest and second fastest swimmers, or do you put all your best swimmers up front, or some other order? And the idea is we relate this to the probability of a gold, silver, bronze, or no medal outcome. And so there were some interesting findings here for swimming in terms of it was pretty good, demonstrated, predicted effectively the outcomes of the 2019 World Championships, and being able to kind of do a risk-reward trade-off, right? What is this ordering that can give you the best chance of a medal without too much chance of missing out on medals altogether? Another interesting finding was that the lowest ranked swimmer in the team tended to step up, tended to outperform their individual performance compared to other swimmers. So there, of course, there was a whole range of work conducted with Swimming Australia. And this is work that's ongoing. At the end of the day, it's all for decision support, right? Providing, massaging all the data and information, and there's more and more of it, and turning it into useful insight to assist decision makers. That's an undercover statistician at the 2019 World Championship trials. I won't go into this in detail here. Besides to say, this was work for the Opals on analyzing game tactics, both movement trajectories, basically with entropy and other machine learning techniques, dynamic time warping, because I wanted to talk a little bit about resilience. Resilience, of course, can have many, many definitions, but one possible definition, and this is in the ecological context, is with respect to if you have some sort of disturbance. It could be training, it could be competition, or something else, right? You have the resistance, the ability to resist loss. You have recovery time, and the uncertainty around that, and also the probability that you don't recover at all. In the ecological context, we were looking at the population of seagrass meadows. And this kind of multi-criteria assessment relates to the resilience of the ecosystem. And our question was, can the risk to resilience of seagrass be mitigated through timing? And the specific disturbance we were interested in was dredging. And so what is quite challenging is that these are complex systems. There's many variables. I'm only just showing a snippet here with lots of feedback loops. So for example, less population, you have less seed, less population to be able to produce seed, less recruitment from seeds, which then results in less recovery. But on the other hand, if you have more population, there's also ability to generate more seed and so on. So there are all these feedback loops. Now, what we were able to do was through a complex systems state space model, be able to incorporate expert knowledge because there's so many variables, there's only limited data that is gathered and available. With experts from around the world to kind of discover these opportunities, these windows in time when you do dredging that can minimize impact, and how that varies across different species. So the species that are fast growing, but they're very weak, so very easy to suffer loss. But if you time it right, you don't disturb their seed, they can come back very quickly afterwards. And the species that are very strong and understanding the thresholds for how much they can take, because if you kill them, they don't really have the ability to come back. So, and then being able to build these global maps of resilience and quantify specifically the risks and the ability to be resilient for different species and locations around the world. And the so what aspect of this is that ecological windows, these windows of opportunity, can enable up to 4-fold reduction recovery time and 35% reduction extinction risk, which is essential for this key habitat, primary habitat for fish, turtles, and also stores more carbon than the Amazon rainforest. Okay, so to wrap it up, given just small examples, I'm afraid, sorry. But what's happening going forward is we have a strategic partnership with the Australian Institute of Sport, Queensland Academy of Sport, the Centre, and then out into the sports network. It's 3 years, a half-time industry research fellow, and 3 or possibly more PhD scholarships. So the idea is we have a core engine of researchers in data science working with core partners at AIS and QAS. And we develop the methods and the modeling ability, and then these PhD students engage with specific sports or domains to be able to create impactful research in applied and methodological. Some potential areas include subsequent events and injuries, so building on our work with the West Coast Eagles and AIS, kind of when to return to play and to minimize or mitigate risks relating to different players and different injuries. And then the flip side of that, performance and adaptation to training. So the more training you do, maybe you might increase your injury risk, but you can also increase your performance. And looking at that in different scales, like within a race, like I talked about with cycling, or over a season, like about the performance test or career. And then also the risk-reward framework, kind of taking a whole systems approach. So that's kind of a quick overview. I'm happy to take any questions and discussion later. Thank you.